Welcome back. So I'm going to just go ahead and give you the overall answers to the convergence questions that you were investigating in activity 6.5.2. So the first question, you investigated the convergence of the integral of 1 over x on the infinite interval from 1 to infinity, and this does not converge. On the other hand, if you look at the integral of 1 over x to the 3/2, this does converge. And in fact, it converges to the number 2. So you'll see that in the course of your investigations here. Part C and D asked you to compare the two functions. One of them, the improper integral, converges. The other one, it does not converge. And so those two questions were asking you to graphically look at the behavior of these functions and be able to describe what's happening here. So I won't actually do these here for you on this video, but I would absolutely invite you, if you have any questions about these, to please send me a note over email or visit my electronic office hours. I'll be happy to talk with you about these questions. And I will be collecting these and looking over your responses here. So please do ask me if you have any questions. What I'd like to do now is just to go through the different cases you'll see with these two different kinds of improper integrals. So in the first case, remember, we have an infinite interval. And so I just want to quickly draw some cartoons to give you an idea of what's happening here. I've actually written the limit definition out here for you. So in the first case, we want to integrate from a all the way out to infinity, some function f. And so what we do is we pick a value b that's larger than a. We find the area between a and b, and then we let b go, we take the limit as b goes towards infinity. In the next case, we have the lower limit of integration is minus infinity, and so here we're thinking we're going from minus infinity to b, and so for a case like this, what we do is we fix some a that's less than b, we compute the area between a and b, and then we let a go to minus infinity. Now let me just make one quick remark here, which is that if this limit is going to exist, so if this limit exists, it has, so I'll just even say if it has any hope of existing, the limit of the function f of x as x goes to infinity has to be 0, right? In other words, this function here has to be getting closer and closer to 0. If it doesn't ever get close to 0 and stay close to 0, then this area is not going to be a well-defined finite number. And similarly, in the second case, in this case, we know if this limit exists, if it has any hope of existing. We must have. Okay, and if this limit, in other words, the limit of these integrals, is going to have any hope of existing, it must actually be the case that the limit f of x as x goes to minus infinity has to also be 0. Okay, and here, if this limit has any hope of existing. Okay, so let me go ahead and just write down what's happening in the bottom case. In the bottom case, this actually combines the two previous cases here, and in this case we have a situation where we have our function f and we really want to integrate over the whole real line. In this case, what we want to do is we want to fix some c, some real number c. So again, when we write this symbol here, what we really mean is in. So we're going to fix c in the real numbers, and then the improper integral from minus infinity to infinity of f of x dx is equal to the integral from minus infinity to c of f of x plus the integral from c to infinity of f of x. So what we do is we can pick any point in the real line and we will split up our integral into two pieces, and this amounts to computing. So this point here is c. We're going to choose some b larger than c, compute that area, let b go to infinity, and then on the other hand we will choose some a less than c. We'll compute the area from a to c, and then we'll let a go to minus infinity. And so here, one big comment is you must compute two limits. Unless you're trying to perhaps exploit the symmetry of the problem. But you need to be fairly careful about that, and we'll see some examples in a moment. All right, so let's talk about the other type of improper integral. And so I'm just going to go ahead and give you the limit definitions and draw you the cartoon pictures of what's happening in these two cases, and then we'll move on to some examples. So in this first case here, we are thinking about a function that is continuous on the interval from a to b, not including a, and we know that there's some sort of a vertical asymptote right at a. So let me just go ahead and draw that in here. So we have a to b is where we want to be taking our integral, and here's my function f that has the vertical asymptote here. And now what we're going to do is we're going to choose some c that's larger than a and less than b, right? And then we are taking the area from c to b, and then we're letting c approach a from above. And so here, notice that that's specifically stated here. This is a one-sided limit from above, and it's because we're trying to take this integral from a to b. So it wouldn't make sense to try to allow c to be on the other side of a here. Okay, let me just quickly draw the other case. You could actually fill this in on your own, so I'm not going to say a whole lot here. So we've got a to b, and in this case, you have the vertical asymptote at b. So let me just draw my cartoon here, and then we're putting in our c. And now c is approaching b from below. Okay, as before, So now then in the next case, we're thinking about a continuous function on AB, and well, continuous except for at some point P in the middle of this interval. And let's suppose the limit as, say, x approaches P from above is equal to plus or minus infinity, and the limit as x approaches P from below is perhaps unbounded. In this particular case, then we do need to use limits. As we talked about before, if f is continuous and there's some sort of a removable discontinuity, so in other words, there's just, if we had f was just had a little hole right here at P, or if f was a piecewise defined function, had a piecewise discontinuity here at P, then we could still define area if f was otherwise continuous. And so we would not need to use the limit technology that we're talking about right here. So this is all, these would not be improper integrals. Whoops. Okay, I seem to be not able to put a dot on my exclamation points. Okay, so let me give you the cartoon of the actual improper case here. So, so here we are assuming that there's some impropriety. So, and in fact, you don't necessarily need to have both of these being infinite in order to have an improper integral. So, okay, so the cartoon of this happening here is we have P and we have A and B, and there's some sort of a vertical asymptote here. It may be the case that actually the vertical asymptote, the function is approaching from the is approaching minus infinity, so diving down near P, but we handle that limit-wise exactly the same. Okay, and in this case, we're going to be picking 2 points here. And you find the area, the area of this, the left shaded area I've drawn in here first, and allow that endpoint to move in towards P, and similarly, you would compute a limit on the other side. So let me go ahead and actually give you a formula here. So I'm going to call this C, and this other point here maybe C tilde. Okay, and so here, if we have this scenario, then the integral from A to B of f of x dx is equal to the integral from A to P of f of x dx plus the integral from P to B of f of x dx. And then here you would compute 2 limits. Separately. And in particular, if either of these limits does not exist, then the entire integral doesn't exist. Oops. If either doesn't exist, then the integral does not converge. Okay, I'm going to go ahead and just zoom in on this a little bit so you can see my writing. The reason we require that both integrals must exist separately is that we don't want to end up in a situation where we're thinking about infinity minus infinity and having to try to work with that. That's always an integral that does not converge. Okay, so let's go ahead and do an example. And we'll think in this case, we'll look at the function 1 over x squared, and we'll try to think about what's happening with that function. So I think the first thing that's always helpful to do is to go over and make a graph of the function and see what's happening there. So I'm going to go ahead and go to Desmos, and I wanted to just start with a blank graph here that you can work in. And so in this particular case, the address is just www.desmos.com/calculator. So you can go here yourself, and we can just go ahead and put this function in together. So let's go ahead and just define the function. So we'll put in here f, and then the parentheses are on the other screen, f of x is equal to, and we're thinking about 1 over x. And notice that you're actually getting a graph as you type it. So here, x squared, and then plus 1. So as we type it, we can actually see that this function looks like it is bounded everywhere. And so yeah, you can actually see it has a maximum at 0, which is where the denominator is the smallest, and so the value of the function is the largest. And so at 0, the function is just at 1. And then as you move out towards the ends, the function gets closer and closer to 0. So this is a case where we might suspect that the function has, that there's a finite amount of area under this function over the whole real line, and we want to investigate that using limits. So we might go ahead here, if you want to add some more to this graph, we might ask for an integral. So let's go ahead and just do that. So int will get us an integral, and the lower limit. So what I'm going to notice here is that this function 1 over x squared plus 1 is an even function, so it's symmetric about the x-axis. So I'm going to choose to think about this integral as being split right at 0, and I'm going to integrate from 0 up to let's call it a variable. Whoops. Back here we'll say 0 to b, and we want f of, whoops, okay, delete f of x, and then we'll just type in dx here. And you can even click then add a slider, and so we can see what happens if we try to integrate from 0 up to 10, and we can in fact make this larger and larger. Okay, now notice the following. If you keep going, it kind of looks like we're getting something kind of close to 1.57. That's some good evidence that this is convergent. And then all of a sudden, if you keep adding zeros, we get to undefined. This is one of these cases where I think Maple is a little better in terms of being able to handle numbers. So we've kind of broken Desmos here a little bit, but we can still get enough information to get some good conjectures. So it's not likely that this went from 1.7 to 1.57 to all of a sudden being undefined, but this is maybe more evidence why we need to investigate formally using limits. So let's go back to our handout and think about this computation then. So what we want to be considering is that this integral is equal to the integral from minus infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. And this is equal to 2 times, because this is an even function, 2 times the integral from 0 to infinity of 1 over 1 plus x squared dx. So we've now really reduced this to just having one limit that we need to calculate. So let's do that. Let's consider the limit, right, as, okay, so we'll just continue this. So 2 times the integral from 0 to infinity of 1 over 1 plus x squared is just 2 times the limit of, as b goes to infinity, the integral from 0 to b, 1 over 1 plus x squared dx. And from your gateway preparations, you'll recall that 1 over 1 plus x squared is an antiderivative for arctangent. So we have 2 times the limit as b goes to infinity of arctangent of x evaluated from 0 to b. And this is equal to 2 times the limit as b goes to infinity of arctangent of b minus arctangent of 0. And so in this particular case, what we're thinking about is now we need to know something about the arctangent function. So if you think about the function tangent, right? This has asymptotes at minus pi over 2 and pi over 2. So when you look at the inverse function, we just flip this function across here. This is going to have horizontal asymptotes at pi over 2 and minus pi over 2 on the y-axis. Okay, so in other words, right, and this is the function arctangent, and the function originally in blue here is tangent. And so what we can see then is that arctangent of 0 is just equal to 0. And so this becomes 2 times the limit as b goes to infinity of arctangent of b. And you can see from this graph that as you go further and further out to the right, the graph of arctangent is getting closer and closer to pi over 2. So 2 times pi over 2. So we're looking at pi as our answer. And so the answer, does it converge, is yes. To what value? It's pi. And let me just go back and say that in our Desmos graph back here, this number here, 1.57, is approximately pi over 2, because here we're just approximating half of the overall integral. So if I had gone back here and said 2 times this and hit enter, then you'll see that that is closer and closer to pi. Okay, I'm going to pause right here and give you some time to work through the integral minus infinity to infinity of x cubed. And so I'd like for you to do this one, include yourself a sketch, and then start up with the next video when you have finished that.